Hello, everybody, and welcome to episode 17 of Tech Bites. My name is Andrew, and I am so thrilled to be your host today for another amazing Tech Bites session. If it's your first time ever tuning in to a Tech Bites episode, just give you a little bit of background. So these episodes are part of our series, Tech Bites, Bite-Sized Tech Talks for Teens. And today's session that you've tuned into, today's episode, is presented by the University of Victoria Department of Electrical and Computer Engineering. So these sessions are meant to be interactive. So if you look to your right, you will see a chat box, which is our amazing moderator, Flight Wizard, who is here to help ensure that your questions get answered. And as we're going through the Tech Talk today with our amazing presenter, Mateo, you're going to get a chance to see some really cool stuff, but also to ask questions and follow along. So this is meant to be interactive. Please definitely check it out and utilize those interaction features. But if you are checking this out on YouTube, you can also respond with questions and comments, and we'll be sure to get you answers there as well. So with all that said, I'm going to introduce you to our presenter for today, who is a graduate student at the University of Victoria in the Faculty of Computer Science. But today he's actually presenting on behalf of the Department of Electrical and Computer Engineering. On a really cool topic that ties in to our Virtual Skills Academy that is starting in a few weeks. So without further ado, I'm going to pull up our good friend Mateo, and we can get things started. So just give me 1 second to unmute you, Mateo.
Okay, hi. Let's get started and we'll get into who I am. So this is through HighTechU and ECE, like Andrew said. Today we'll be talking about how to use a method called I2C for displaying on an LCD the status of an ambient light sensor. So about me, you may have heard this last week, but I have a bachelor's in electrical engineering. I worked as a design engineer over the summer last year, and I'm currently completing my master's in computer science here. So let's get into the topic. So for this week, I'll be going through my slides, and then after each slide, I'll be shifting over to TinkerCAD to work on the circuit that we'll be building together. So to start off, we'll be using a photodiode. As this slide says, a photodiode converts light to current and is similar to the structure of an LED where there's an anode and a cathode side. So let's shift over to TinkerCAD. So we're using they're not. I'm not sharing my screen, that's why. That's embarrassing. Okay. Perfect. Okay, so yeah, so as this showed, I2C for ambient light. So for photodiode, we'll be switching over to TinkerCAD. So if we go over to TinkerCAD, we have here our parts, and we're using a photodiode. So first, let's make a breadboard. This will post this. And our Arduino, and get a photodiode. So we have photodiode here. Rotate this. Okay, and you zoom in, you see there's the anode side and the cathode side, shown through the plus and minus. So we are wanting to get this as an input. So first, let's hook this up. So for the anode, you have what we'll be doing, we have the anode side connected to ground. This will be our ground line, which we can set up as ground by connecting it to the Arduino's ground. We then have the cathode side going into we could do it where we just go directly into our analog input. But instead, what we'll be doing is we'll be using something called a operational amplifier, which will basically allow us to get the sensitivity of our output from this, which you may have seen last week. So let's do an amplifier. So this is a 741, which is the most basic and usually cheapest version that you'll find on the market. So there's 8 pins, but we'll only be using 5 of them. So the first pin we'll be using is the negative input, and that's connected directly to the cathode side of the photodiode. The next one is the 3, which is the positive input that's connected to ground. We then have 4, which will be the lower threshold for what we can have as the output. So that will be 4 connected to ground. We have that here. Then we'll have 7 connected to power. So if we have 7 here, power, connect these power lines, connect power like this to the 5 volts. We then have 6 as the output. So 6 will be what's going into the pin. So we're going to use a 0. And then between 6 and our negative input, we have a resistor. So for the resistor, I'll be using a 12K, which gets us roughly the range that we want. So I'll just be connecting this 12K, and I'll connect this over to 6. So like this. So this is our op amp and our photodiode. So going back to the presentation, we have a quick overview of the pins of a Arduino. So analog and digital. I can actually get rid of that. Digital pins go between on and off, high and low, and analog pins have 0 to 255. If we continue, what we'll be doing today is something called I2C programming, which is a method of programming which uses 2 wires it's basically 2 lines, serial data and serial clock. The clock is basically a synchronous clock, which allows for the data to be sent at intervals, and the data is where we send the data. And this will be connected to another Arduino. So let's do that. So let's add another Arduino. This here. So these, move this up higher. These pins that we'll be using are the A4 and A5, which will connect together. And these will be our serial data and our serial clock. And this will be done through something called the wire library on the for the I2C programming Arduino library. So what we have to do is that there's a common ground between the 2 boards, and that means the ground of the 2 boards have to be connected, and also the 2 pins are have to have a pull-up resistor. So what that means is that the way that these work is that when we want to send data, the serial data line goes active low to say that we're starting to send data. And while we can have the this work without the pull-up resistors, what that leaves it in is kind of like a gray area where we don't really know what the value at that pin is. And so by putting a pull-up resistor, we're basically saying it is high until we pull it low. So let's connect those. So the pull-up resistors, what we can basically do is connect each of these pins to here. So you can get this. And just connect 2 resistors to ground. And what you put for the resistors determines how much data you can send. So we'll just use something called about 2K, which is usually allows you to send more data, but that won't be relevant because we won't be sending a large amount. What is 2.2? And to make sure that these are the same, so like connect the grounds. Okay, so what we have here now is we have two at megaboards that are connected for the I2C, which means that these will be, this one will be the master and this one will be the slave receiver. So this one will receive the data. So what we'll be doing next is we'll be connecting an LCD display, which will basically show the output of how this will be working. Okay, so let's go back to here. So this is just a overview of what I was showing before. So you have a pull-up resistor between the two serial data line, serial clock line, and the clock line synchronizes the two boards for when the data is transferred. So here's the LCD display we'll be using. So the LCD display has 16 columns, 2 rows. So each row we can only send 16 letters. We're sending letters or numbers. And it uses a library called the Liquid Crystal library. So what we'll be doing is that we'll be operating this in something called 4-bit mode. And what that basically means is that normally if you want to send a what you want to be printed out on one of the column and rows, it sends 8 bits, and those 8 bits basically give you an ASCII character. But that requires a lot of I/O pins. So if we first go back and get this LCD display, we see that there's 8 pins. So each of those in 8-bit mode would have to be connected to one of the pins on here, but that requires a lot of the input-output pins. So instead, what you can do is use 4-bit mode. What 4-bit mode means is that we'll be sending basically 2 sets of 4 bits at a time. So the first 4 bits will go and be the first the latter half of the 8 bits, and then the second set will be the first 4 bits, and that usually adds a little bit of latency, but it's not too noticeable. And I actually have a graphic to show this. So if you see here, we have 8 bits, and for the 8-bit mode, it sends all 8 bits at once, and you get your letter when the enable pin goes high. And with the 4-bit mode, you send 4 bits at a time, and you have to use 2 enables at a time to get the full letter. So let's go to making this work. So let's add another breadboard. So we'll basically put this here. Okay, so we see a lot of pins here, which we will be working with. So first, let's connect the grounds. And add ground here and 5 volts here. So the first pin is just ground, so we connect that to ground. Second pin is VCC, which is our power. Next one is contrast. So we won't be changing the contrast of the LCD display, so we can just push that to ground. It won't be important. Register select is basically there's 2 registers. There's the command register, which is basically when you send a command to the LCD display, you're basically saying what you want it to do. And the data register, which is where you send what you want the LCD display to store for data for what it's going to be outputting. So this connects to pin 12 of our Arduino. So let's connect that. We go up. and over, we get to pin 12. Next, we have read-write. So this determines whether or not we'll be writing to this LCD display or reading from it. We'll be writing to it, so we connect it to ground, because low is ground. Low is write. And then we have enable, which is basically, as we saw in the graphic, when enable goes high, data will be sent. So we can connect this to the pin 11 of our Arduino. Zoom a bit more. Okay, so then, as was mentioned, we're only using 4-bit mode, so we can use these four, DB4 to DB7 to control our LCD display. So let's connect those to pin 2 through 5. 2, 3, 4, and 5. And the last two pins, this LED, this is basically the backlight for the LCD display. So similar to the LED that we were using in the last presentation, the current's roughly the same, so we can use the same resistor. So in order to get roughly 0.1 amps, 0.01 amps, 10 milliamps going through the as the backlight, use a 220 ohm resistor. So if we do a resistor and connect it to ground, set it to 220 ohms, and connect the LED to that, and then we just have the other side to power. Okay, so now we have our LCD display set up. We have our photodiode connected to the op-amp, so we get the sensitivity we want. We can now start with the code. So I have the code pre-done, but we'll go through it. So if we go here, we can copy this in. So we have our master. Switch to text. Okay, so if we look at here, we're using the wire library, and we're setting the photodiode as A0. We basically say that we want to use the serial monitor, and we're using at this baud rate. And we're setting the photodiode pin as an input. And we start with this wire.begin. What this basically is saying is that we're going to be using the library, and we're not putting a address, which means this is going to be used as the master. We then set a byte X. So how I have this basically set up is that we read the value from the A0 pin, and if we get, it prints it, and if it's greater than 155, which is roughly half the way up the photodiode, it gives you back a 1, else it gives a 0. We then begin a transmission, and what this works is that we're basically saying that we're going to be transmitting to slave device 4, which is the address we'll be giving to this at Mega, and we're going to be writing to it X, and then we're going to be ending that transmission. This is sent 1 byte at a time, and for this, it's being sent at just 1 byte, and for each of those, each clock wave is basically sending 1 bit. And if we want to send more than 1 byte, we can change this line. There's a different form, which basically you say how many bytes you're going to be sending and what you're writing to it. So we can then go to the slave code. So we scroll down of here. For here, we're basically saying we're using the wire library and the liquid crystal. So if you see here, we're basically saying the display is using these 6 pins. If we had wanted to do 8-bit mode, we would have included the other ones. We're then saying that we're going to start the LCD display, turn it on, and we're using 16 columns and 2 rows. This says that we're starting this device and with the wire library, and we're using this as address 4. And then it's waiting to basically receive an event. And this delay is basically going to be checking every 1/10 of a second to see if an event has occurred. So this event, what it's doing is it's going to read from the wire, whatever int we are sending. It's going to print it for us just to see. And if it's 1, we're going to say that the photodiode is high, greater than the threshold. This is basically saying we're starting at row 1, column 0. And if it's low, we're going to say it is PD low. So let's see this work. So if we start simulation. Something up. Let's see. Okay, so what this is showing is that we have the LCD display on, but it doesn't seem to be setting this low, which is weird. So if we want to figure that out, we also see that when we turn that high, it does not change that. I have a pre-done version that I can show. It is the should be exactly the same, but if we go to that, you see circuit is pinned the same, and we see that when we start it, it's going to say PD low. It's going to stay on for 2 seconds, and when we shift this to high, it will change it to PD high and turn off. Apologize for the error in the other circuit. And if we go back to the presentation, that is what I have. So if there are any questions, I'm able to answer them. And thank you. Yeah.
Fantastic. Thank you so much for that awesome session, Mateo. And if you're interested in learning more, so Mateo referenced back to a few other presentations, our entire series, A Tinkerer's Introduction to, are all found on our YouTube channel. So you can check us out on YouTube. Just search for HighTechU. There's also going to be a link in the stream chat if you're interested in checking that out. You can also find links to all of these on our website, hightechu.ca. If you're interested in finding out more about when we run these sessions, you can be sure to subscribe to our YouTube channel to see when we upload these videos. You can also follow us here on Twitch. And of course, you can always find out more information on HighTechU at hightechu.ca. So on behalf of all of us here at HighTechU, on behalf of all of our sponsors and funders, including Coast Capital Savings, the Faculty of Engineering, and the Department of Electrical and Computer Engineering here at the University of Victoria, thank you so much for checking out our Tech Bite today. This is obviously the last in our A Tinkerer's Guide to series, but we are going to be really excited to come back with some brand new content very soon, and hopefully in the next couple of weeks we are going to be hitting our 20th episode of Tech Bites. So I'm gonna spin back over to you just for a second to wave goodbye, Mateo, and then we're gonna say goodbye for today.
Sounds good.
There we go. Back over to you.
Okay. Thank you for showing up. I'm glad I was here to show you guys these little tidbits, and looking forward to doing this again.
Thanks for coming, everybody. And remember, stay healthy, stay safe, and we'll see you next time.